Hey everyone, welcome back. Today we're taking a deep dive into how we evaluate large language models, those LLMs that seem to be everywhere these days.
They are pretty amazing, right?
Yeah, I mean, they can write, so you can answer questions, even code, but
Yeah.
uh, how do
Yeah.
we actually know if one is better than another?
Yeah.
It can't just be about who gets the highest score on some test.
Nope.
I mean, think about it. Imagine you were trying to pick the best ship, like, say, a galleon versus a dreadnought
Mhm.
for a long sea voyage. You wouldn't just look at which one has a higher top speed, right?
Exactly. There's so much more to it than that. You'd
Yeah.
want to know about their reliability, how they handle rough seas.
Right, exactly. And, like, how they perform in different conditions.
For sure. Calm waters, everything.
Yeah.
Same with LLMs. We need to go deeper. We need to look beyond just those surface level scores.
Well, that's what our sources for this deep dive are really emphasizing.
Yeah.
They're saying a lot of those traditional LLM evaluations are kind of like saying, well, the galleon won that one race, so it must be the better ship.
Right. But that doesn't tell the whole story.
Yeah, without considering all those other factors, like you said.
It's like we need to be thinking about these evaluations more like scientific experiments.
Okay, I like that.
Yeah, and just like in any good experiment, we've got to use the right tools, the right statistical tools
Oh.
to really understand the results. Can't just rely on gut feelings,
Yeah.
or cherry-picked data.
Right, we need to be confident in the results.
Exactly. Like, are the differences we see between these models, are they actually meaningful, or is it just random chance?
Okay, so where do we even begin with this? Like, how do we bring that kind of scientific lens to something as complex as an LLM?
One of the key things to understand here is this idea of a superpopulation.
A superpopulation, okay.
Yeah, so think of it this way.
Right.
Imagine like a vast ocean of all the possible questions you could ask an LLM.
Okay, I'm picturing it. This huge ocean of questions.
Yeah, that's our superpopulation. Now, any evaluation that we do, any test, it's just like dipping a little net into that ocean and catching a sample of questions.
I got it.
Right.
So we're only testing on a small selection of questions, not every possible question.
Yeah, exactly. You're not going to test on everything.
So then how do we make sure that small selection is representative of, like, the whole ocean?
That is the question, right? That's where things like confidence intervals come in.
Okay, confidence interval. I've heard of those, like from election polling.
Yeah,
They give us a sense of, where the true score probably lies.
exactly.
Considering that our sample might not be perfect.
Exactly. Acknowledging that there's some uncertainty because we just have this small sample.
Okay, so just like we wouldn't declare a winner of an election based on exit polls alone,
Right.
we shouldn't jump to conclusions about LLMs based on a single score.
Exactly.
We need that confidence interval to, like, give us a sense of how much wiggle room there is.
For sure, yeah. So how do we actually calculate these confidence intervals for LLMs? Well, it starts with understanding something called standard error,
Okay.
which is basically a measure of how much the scores we get from our sample
Okay.
might vary from that true score, that true score out there in that superpopulation.
So the smaller the standard error, the more confident we can be in those results,
Oh,
right?
yes, absolutely.
Like our net is catching a more representative sample of the, the fish.
Exactly, yeah. So once we have that standard error, then we can actually calculate that confidence interval, and usually it's set at 95%.
95%. Oh.
Okay, which means that if we were to repeat this evaluation a bunch of times, 95% of the time, that true score would fall within that range.
Got it. So it's like saying, hey, we're pretty sure the dreadnought is faster, but there's a slight chance the galleon could still surprise us in a different race.
Yeah, I love that analogy. It really captures it well.
Yeah.
And, being upfront about that uncertainty, that's really crucial, especially if we're making, big decisions based on these evaluations.
Absolutely. Choosing the wrong LLM could have real consequences depending on what you're using it for.
For sure.
But confidence intervals, those aren't the only thing we got to consider, right?
Right.
There are all sorts of things that can skew the results of these evaluations.
Right. There are all sorts of things that can kind of mess things up.
Like what?
One of the big ones is
Okay.
clustered questions.
Clustered questions. Okay. I'm not sure what that means.
Yeah, so think about our fishing net again.
Okay. Back to the net.
Imagine if it catches a whole bunch of fish,
Uh-huh.
but they all tend to swim together in a school.
Okay. Yeah, I can see that.
That's kind of what happens with clustered questions.
Okay. So give me an example, like asking a bunch of questions about the same paragraph.
Yes, exactly.
Or like the same question, but in a bunch of different languages.
Exactly. Or maybe questions that are all related to the same topic or something like that.
Okay, I see. So they share some underlying characteristic.
Right. And the problem is these clustered questions, they're not really independent samples from that whole ocean,
Hmm.
right? They might be easier or harder than average.
Because of that shared characteristic, right?
Exactly. So it's like assuming that all those fish in that one school represent the entire ocean.
Right, when they might just be one specific type of fish in that area.
Exactly. And because of that, we might underestimate how much variation there actually is
Mhm.
in how that LLM actually performs. We might think our results are super precise when they're actually more like looking through blurry binoculars. We got to adjust our calculations to account for this clustering.
Okay, otherwise we could get some misleading conclusions.
Yeah, exactly. So clustered questions, they're kind of a hidden trap in LLM evaluations.
Okay, so we need to watch out for those and use the right techniques.
Yeah, exactly. And luckily, there are ways to do that, like using what's called clustered standard errors,
Okay.
which we can get into a little bit later.
Okay, sounds good.
Yeah, but I think for now, the important thing to remember is even with the best tools,
Uh-huh.
LLM evaluations are still going to have some level of noise. We're dealing with really complex systems here.
That's true. So are there any tricks we can use to try to, reduce that noise and get more reliable results?
There are,
Okay, good.
and some of them are surprisingly simple.
Okay.
One of the easiest and most effective is called resampling. Remember our analogy of the net?
Yeah, dipping the net in the ocean
Resampling is like dipping the net multiple times
multiple times for each question.
for each question, yeah.
So instead of just asking a question once, you ask it multiple times,
Yeah.
even if it's the exact same question.
Yep, even if it's the exact same question.
Okay, but why would you do that?
Well, because each time you ask, the LLM might give a slightly different answer,
Huh.
even if the question is the same. That's because there's a bit of randomness in how those LLMs actually generate their responses.
I see. So it's like casting a wider net to get a better sense of the variety of fish in a spot.
Exactly, you got it. And so by averaging the scores across all those multiple responses,
Uh-huh.
we can kind of reduce the noise that comes from that randomness. It gives us a more stable measure.
Okay, so resampling is like smoothing out those bumps
Yeah, smoothing out the bumps.
and getting closer to that real signal.
Exactly. What else can we do? Another great technique, especially for evaluations that don't involve super complex reasoning, is by analyzing something called the next token probabilities.
Okay, next token probabilities.
Yeah.
Now we're getting into the nitty-gritty of how LLMs work.
A little bit, yeah.
So tell me more about these.
So think about it like this. When an LLM is generating text, it doesn't just spit out a whole answer all at once.
Okay.
It builds it up like one word or even one character at a time, predicting what should come next based on what came before.
Okay, yeah, so it's like writing a sentence, one keystroke at a time, always predicting that next letter.
Exactly. And we can actually see the probabilities
Mhm.
that the LLM assigned to each possible next token
Uh-huh.
in that sequence.
So instead of just scoring the final answer as right or wrong, we can actually see how confident it was along the way.
Exactly. You're like peeking behind the curtain to see how it's thinking.
This is cool.
Yeah.
So how does that help us reduce that noise, though?
Well, because those next token probabilities, they tend to be more consistent
Okay.
than that final output,
Okay.
which can, vary a bit due to that randomness we were talking about.
So we get a clearer picture of what the LLM actually knows,
Yeah,
even if the final answer isn't always perfect.
exactly. You got it.
Okay, these are great.
Yep.
What's that third trick for reducing variance?
So this one's particularly useful when we're comparing two different LLMs, head to head.
Okay.
It's called paired analysis.
Paired analysis.
Mm-hmm.
So this is where we finally put our galleon and dreadnought up against each other.
Exactly.
Okay, tell me everything.
So instead of just looking at their overall scores,
Uh-huh.
paired analysis zooms in on the differences in their performance on each individual question.
So you see how much better or worse one did compared to the other on each question.
Exactly.
Okay.
And the advantage here is it can help to cancel out some of that noise that affects both models equally.
Oh, I see. Okay, so if a question is just really hard,
Yeah,
both LLMs might struggle with it regardless of their overall abilities.
exactly.
It's like comparing how they both handle rough seas.
I like it. Yeah,
If they both get tossed around equally, it doesn't tell us much.
exactly.
But if one consistently sails smoother, then that tells us something.
Yeah. So by focusing on those question-level differences,
Okay.
we reduce that variance in our comparison,
Yeah.
giving us a more sensitive measure of the real difference between those two models.
So it's like controlling for weather conditions or something.
Yeah, exactly, to get a more accurate comparison.
Yeah.
And here's where it gets even more interesting.
Okay, tell me more.
The effectiveness of this paired analysis, it actually depends on how much those two models agree.
Agree on what?
Like which questions are easy or hard.
Oh, okay. So if they tend to agree, that actually makes the comparison more precise.
Yes, exactly.
Yeah, but why?
Because the more their performance is correlated,
Hmm.
the more that shared noise we can cancel out.
Oh, okay. So it's like observing that both ships struggle in high winds,
Yes.
but sail smoothly in calm waters.
Yeah.
That correlation helps us to hone in on what's really making the difference.
Exactly, you got it. So paired analysis can be really powerful for spotting those subtle but important differences.
Paired analysis. Got it. I'm starting to see how all these techniques can give us a much more rigorous picture of how to evaluate LLMs. This is great.
It is.
This is really helpful. But, sometimes I see people trying to game the system a little bit.
Oh, yeah?
Yeah, like messing with the LLM settings,
Okay.
try and force it to give more consistent results. Is that a good idea?
So you're talking about adjusting what's called the temperature parameter, right?
Yeah, the temperature.
Yeah, it's tempting to think that by lowering the temperature, which makes the LLM's responses more deterministic, that it'll lead to less variance.
Right, less random, more consistent answers. So what's wrong with that?
Well, here's the catch.
Yeah.
While it might seem like you're reducing variance, you might actually be introducing bias into the evaluation.
Bias. Okay, explain that. I'm not sure I get it.
Okay, so think of it like this. Lowering the temperature, it's kind of like forcing that LLM to always choose the most obvious, most predictable path. Even if there might be other, more creative or more insightful options out there.
It's stifling its ability to explore,
Exactly. You got it.
Yeah.
It can really distort our understanding of what that LLM is truly capable of.
It's like telling our ship's captain to always stick to the most well-charted course.
Yes.
Even if there might be a faster or, a more interesting route.
Right, exactly. And you might miss out on seeing, its full potential. And not only that,
Right.
reducing that temperature can actually increase the variance of something called the conditional means.
Wait, hold on. You're saying lowering the temperature can increase variance. I thought it was supposed to do the opposite.
I know.
That's counterintuitive.
It is, yeah. But remember when we were talking about those conditional means?
Yeah.
Well, they represent the true difficulty of each question, considering all the possible ways the LLM might answer.
Okay, yeah.
So lowering the temperature can actually make the differences between those conditional means bigger,
Oh, yeah.
making some questions look way easier or way harder than they actually are.
So it's like creating a false sense of separation between the easy and the hard questions.
Exactly. You got it.
Okay, don't mess with the thermostat. Got it.
Yep.
Let the LLM do its thing. But now that we've talked about all these great techniques for reducing that variance and getting more reliable results, I want to hear about how we actually put all this together to compare two LLMs head-to-head.
Okay, yeah. Well, remember how we were talking about paired analysis
Yeah.
being such a powerful way to compare these models?
Yeah, because it cancels out some of the noise.
Exactly.
Okay.
That's a great place to start. So we can actually use either unpaired or paired analysis, depending on whether both models were evaluated on the same set of questions or not.
So unpaired is like comparing the galleon and dreadnought's average speeds from separate voyages,
Yes.
while paired is like watching them race side by side.
Yes, I love your analogies.
They really help.
Yeah, they really paint the picture. And so, like we talked about earlier, paired analysis is generally more powerful because it cancels out some of that noise.
Right, exactly.
Yeah.
Like controlling for the conditions to get a fair comparison.
Exactly. And with paired analysis, we can actually calculate a confidence interval for the difference in those model scores, just like we did for a single model earlier.
Okay.
This tells us how confident we are that that difference we observed is real and not just random chance.
Okay, so we're not just looking at who wins, we're looking at how much they win by
Exactly.
and how confident we are in that difference.
You got it. It's like saying, the dreadnought beat the galleon by a statistically significant 5 knots. So we're pretty darn sure it's the faster ship.
Okay, I like that.
Yeah.
Yep.
And what's really cool is by applying all these statistical techniques, we can sometimes completely overturn conclusions that were made based on just like a quick glance at the results.
Wait, so you're telling me those first impressions can be deceiving?
They can be, yes.
Okay, and here's an example.
All right, so remember our hypothetical models, the galleon and the dreadnought.
Of course.
Let's say we have results from 3